Welcome back to another episode of Stat 568, Design and Analysis of Experiments. We are back today and we'll be discussing multi-factor experiments. We're moving into chapter 2. It's a new day. Let's see what we got to look at. So in our first lecture on multi-factor designs, what we're going to be looking at is the complete randomized block design. So we're going to take one-way ANOVA and we're going to transition into the idea of doing one-way ANOVA with a blocking factor. We're also going to look at the Tukey 1 degree of freedom test for testing for interactions, because sometimes factors interact and we want to know if they're going to be doing that. So let's go take a look at that. Welcome back to another lecture of Stat 568, Design and Analysis of Experiments. In this chapter that we're beginning today, this is chapter 2 in my notes, we're going to be looking at multi-factor experiments. So now we can get into the real meat of the course, because the first few lectures are really just to set the stage with some of the terminology and the idea of one-way ANOVA. But to be honest, one-way ANOVA, it's pretty boring. There's only one factor we can work with. Now we're going to consider so much more complications that can come on top of this. When we have multiple factors, how do we deal with them? Are they nested? Are they related? Do we randomize them differently or the same? And how do we put all the pieces together? Can we even test all the treatments that we want to test? These are some of the questions we'll be looking at going forward. But first, what we're going to do is start with the idea of a complete randomized block design. So we're going to extend the idea of one-way ANOVA by keeping a single experimental factor, but now adding on a block factor. So this would be like, for example, if I'm running a medical trial, I could consider multiple tests of different medication on my subjects. But it might be better to add a blocking factor, such as the age of the subjects. So now we can have the older ones and the younger ones in separate blocks for testing. And that's what we're going to look at now. All right, so the first thing we'll be talking about is the idea of a randomized block design. So randomized block design. And as I mentioned, the idea is really to do one-way ANOVA, but with a blocking factor. With a blocking factor. All right, so in the very, very first lecture of this course, I introduced the idea of a block factor, but I only introduced it by defining it and not really going into detail. All right, but the rough idea, the idea is to group similar subjects together to reduce variation and to get more statistical power and to get more power for testing whatever experimental factor we want to test. The experimental factor. There we are. So mathematically, a block and an experimental factor act the same way, but the way we treat them in statistics is different, the way we interpret them. Typically, for a blocking factor, we aren't necessarily interested in the outcome. We're really just interested in taking the variation of the blocking factor and removing it from our analysis so that we have more statistical power to focus on the experimental factor. So again, for example, as I kind of wrote out before, example, we could have an experimental factor, which could be something like, say, medicine 1, 2, 3, or maybe there's also a placebo in there. But the idea is maybe we have different types of medication that we want to test. Maybe it's blood pressure medication. We want to see if it lowers the subject's blood pressure. Maybe it's something else. But this would be an example that we might want to test, and we can use a one-way ANOVA to do that. But then we can also consider blocking factors. You can say block by really whatever you can imagine, right? You could block, like I mentioned, by age. You could block by sex. You could block by, I don't know, what else can you block by, right? Then in some sense, you could block by so many things. You could block by, let's say, smoking status. Are you a smoker or a non-smoker? Right? You could do so many different types of blocks, and the main idea would be to reduce variability. So, for example, I roughly think I recall that smoking raises your blood pressure. Don't quote me on that if I'm wrong, but let's say smokers have, on average, higher blood pressure than non-smokers. Then what we can do is, by blocking and having a separate group of smokers and a separate group of non-smokers taking our different blood pressure medications, we can remove that variability and then focus in on the effect of the medication in that subpopulation. So then mathematically, what is this going to look like? Well, the equation that we get would be look something like this. I should say the equation, or the model that we'll be trying to fit, is going to look like Yij is mu, again, our global mean, some beta, which is going to be our block factor, beta I. We're going to have tau j for our treatment factor, or treatment effect, and then we're going to have epsilon ij for our random noise. So what do we have here? Let's just write that all out, right? We have our global mean, the average over the entire population that we're studying. We have the ith block effect, whatever that corresponds to. In this case, we're just treating one block factor and one treatment factor, but of course we can generalize this to have multiple treatments, or I should say experimental factors, but multiple treatment and multiple blocking factors. So again, you could have, old men who don't smoke and things like that. So the blocks can become much more complicated as we go forward. This tau j would be the jth, I'll say experimental factor. And this is just going to be our random noise. Noise, which, as usual in this course, we will assume is IID normal 0 sigma squared, so constant variance throughout all the different blocks and treatment groups. So if I should also index and say for I equaling 1 to B, so we have B blocks, and for J being 1 to, I think I used K as before, K. So we have a total sample of size capital N, to use the same notation I was before, of B times K. And this is in the case that we also do not replicate this. So this is a very specific case to consider. This is I'll say specifically, what we have here is a complete, unreplicated, randomized block design. I guess we're assuming it's randomized. It should be randomized. So what do all these terms mean? Well, the complete is just basically telling us that every experimental factor is tested the same number of times in every block of times in each block. And the idea of unreplicating it means that it's going to be tested exactly once. Unreplicated means each experimental factor is tested exactly once per block. So this is a way that also keeps the sample size smaller. If we're running our medical experiment and we have, let's say, 3 medications and we have maybe 2 blocks, the smokers and the non-smokers, in this specific setup, we would only have a sample size of 6, which is actually quite small. And we could replicate that, right? We could have, instead of just a set of 3 smokers and 3 non-smokers, right? We could have maybe 6 of each, or we could have 30 of each, and then we could test that. So we could replicate this a bit. But in this specific setup, we're just assuming that in every block, we see every treatment exactly once being tested. And vice versa, you can flip that and say how do we phrase that? Every treatment gets one of the block factors. And this is the idea of complete. So later in this course, we'll be talking about incomplete block designs and what happens when you can't test every single experimental factor level within each of the blocks, because sometimes it's not possible to test every possible combination. In this case, we're just assuming it is. And of course, you can always replicate this if you have the time and money and funding to do so. Yeah, so I think I pointed that out here in my notes. I said, if replicated, say, n times, then the total sample size becomes capital N, which is going to be n times little b times little k. Right. We would effectively take our complete unreplicated block design and then just do it n times with new subjects. Yes, and I should also emphasize, we emphasized complete and unreplicated, but I didn't talk about randomized. So randomized basically means assign treatments. I'll say treatments at random within each block. So strictly speaking, if we were to run one of these experiments, we would want to randomize the assigned, let's say, medications for each of our blocks. So if we had, let's say, old and young, smokers and non-smokers, we would have 4 different blocks to work with. And within each of those, we would want to randomize the medication being applied. All right, and yes, so we end up with the same idea as before with respect to the concept of constraints or contrasts, because now if I'll say recall from one-way ANOVA, that to actually estimate all of the terms, we need a contrast / constraint, linear constraint, I guess to be precise mathematically, a linear constraint to estimate all parameters, or I guess all parameters except for the one that gets lost due to the linear constraint, to be, again, precise. So we have something that looks very similar to what we have before. I'll say, for example, what we can assume is that, say, the sum of the beta I is going to be 0. This is I from 1 to little b. And the sum j from 1 to k of the tau j is going to equal 0. This is one example. This is that sum to 0 constraint. As we mentioned in a previous lecture, you can do other things like set the final, set one of the categories, one of the betas, and one of the tau's to be 0. As long as you just have some linear constraint in there to allow you to estimate all of the parameters mathematically. Which is always good to know, because if you actually try to compute everything in R, you'll notice that you'll be missing one of the parameters, and that can often be confusing when you first see it. Anyway, we also have, as usual, the sum of squares decomposition. And this is going to lead us right back into the idea of ANOVA. And our F tests and all of those things that we're going to be doing throughout this entire course. So in this case, we're going to do something, again, very similar to what we did last time, but we're going to add in another term. So nothing, say, more sophisticated than what we did before. We just have a lot more terms or I guess another term or two to deal with. So what we write is we write this equation out, which again on its surface looks kind of silly, because all we're basically saying is I can write Yij by adding and subtracting a bunch of sample means here. No. Sorry, here's some random noises in the background, though I don't think the mic will pick them up. Anyway, so we have something that's going to look like this very long, drawn out equation. And I think, oh yes, good, everything should cancel out. Otherwise, I missed a term. Right, so this is our big sum of squares decomposition. Well, it will be once I square it and sum it. Right, what we end up with is something that's going to be the sum of Yij minus y bar dot dot squared. And what we're going to do is write that as the subsequent three pieces all summed and squared over all of the, over all I and all j. So what we end up with is something, well, okay, for the first one, let's just take a moment and kind of note that here we have our block, here we have our, I'll just say treatment, and here we have our residual piece, and this is the global mean in the front. Okay, so now that we have these pieces, again, we can sum them and we can square them and we can sum them in that specific order. And what we end up with, I should have put a double sum here first, because we want to take j from 1 to k and we want to take I from 1 to b. When we sum the block term, there is no index j. We've already, in some sense, averaged over index j in that second term here. So what we end up with is just, well, a k times the sum of I from 1 to b. It's super easy to mess up the indices here. So let's see if we can get through this together without making too many mistakes. All right, so that's the first term. The second term is going to be a b because we've already summed over all i's from 1 to b. And then we're going to take j from 1 to k, and we're going to sum y bar dot j minus y bar dot dot squared. And then the last piece, which I'll write on the next line, just so I don't run into myself here, is going to be the double sum over I from 1 to b, j from 1 to k, and we're going to sum this entire last thing squared. Now, if you are, paying attention to the idea of squaring both sides of this equation, you might think to yourself, well, wait a minute, there's all these cross terms, right? Because if I square something like a plus b squared, I'm going to get an a squared, I'm going to get a b squared, but I'm also going to get a cross term, a plus 2b. So then you might think to yourself, well, why are there no cross terms in this sum of square decomposition? The reason is they all cancel out after we sum over all I and all j. And you can check that yourself if you want to. It's not the most interesting thing to do, but you can do that if you really want to identify that all of the cross terms will in fact cancel out. Now that I look at my notes, I realize there's a missing square on the total sum of squares there, so I need to fix that. I also need slightly more room here, so we'll slide down my little a squared plus b squared, because what we need to do is identify that we now have a sum of squares decomposition where this first guy is the total sum of squares as usual, and we're decomposing it into three pieces. Those pieces would be the block sum of squares, the treatment or experimental sum of squares, and the error sum of squares or residual sum of squares, depending on which terminology you want to use. So this here becomes we're taking the total sum of squares and we're breaking it into three pieces. And this is a really key thing. So first of all, this goes back to the last lecture on Cochrane's theorem, the idea that now I have three sums of squares. They each are quadratic forms, and we can think about them in the context of Cochrane's theorem for statistical hypothesis testing. But more intuitively, what's really neat about this is that we're really taking the total variation, that is the total sum of squares, and we're breaking it into different pieces. We're breaking it into the variation coming from the block factor, the variation coming from the experimental or treatment factor, and the variation that is unexplained by those two things, that is the error sum of squares. So it's really a way to decompose the variation in our data into three disjoint pieces that, thanks to, again, things like Cochrane's theorem, we know are orthogonal in some mathematical sense to each other, so we can consider them all separately. And then this, of course, leads to our hypothesis tests. So, good, yeah, we should have just enough time to get through that, and then we'll move on to the next section. All right, so the hypothesis tests that we want to run, right? It's typically, I mean, we can always test the block factor. Typically, we don't necessarily care about testing the block factor, but it's more so there just to give us more power for testing the experimental or treatment factor. But mathematically, we could just test it just as we did before. But moreover, what we really want to do in this case is test for whether or not all the levels of the treatment are the same, or if at least one treatment differs from another. So mathematically, there exists a J1 and a J2 such that tau J1 is not equal to tau J2. Just saying that there's two different treatments that give us different responses from our model. And what we get here is we get the exact same F statistic. Well, I shouldn't say the exact same F statistic. We get an F statistic as before, with a slightly different setup for the degrees of freedom. So basically, we test this with an F statistic. Thanks again to Fisher and Snedeker statistic, which in this case is going to look slightly different than before. The numerator is still going to be the same. It's going to be our treatment sum of squares divided by its degrees of freedom. So then you have to figure out, well, what are the degrees of freedom here? And it becomes a little bit more complicated. What I'll do is I will just write it down here in the F statistic, and then I'm going to write down the ANOVA table, and then we'll talk a little bit more about where the degrees of freedom are coming from. but the numerator is going to look basically the same as we saw last time for one-way ANOVA. The denominator is still going to be the air sum of squares, but things change slightly. And what happens now is that we have the degrees of freedom being b minus 1, k minus 1. So the degrees of freedom in the denominator have now changed a bit. Again, we'll talk about that in a second, but what we assume is that this statistic follows an F distribution with degrees of freedom corresponding to the numerator and the denominator under the null hypothesis. Again, this is always under H naught. Hence, if we're not in the null setting, we can then detect significance by comparing our observed statistic to the F distribution. If we are to, say, write out the entire ANOVA table, the table will look something like this. We'll have a block, we'll have a treatment, and we'll have our residuals. And what we get when we look at degrees of freedom is, again, the way I like to think about this intuitively, if I go back up to my equations here, it's the number of things in that category minus the number of estimated parameters. So in the treatment case, we have k treatments and we're estimating one global mean, k minus 1. In the block case, we have b blocks and we have one global mean, so we have b minus 1. In the residual case, what we have, and this is a little bit more confusing, but if we look at the residuals here, at the top of the screen, we kind of have b times k observations, and then in a way we are subtracting k category means for the treatment, b category means for the block, but then we're adding on one global mean in sort of an inclusion-exclusion sort of way. So it's a little bit confusing, but I'll write that down to show you where this comes from. Anyway, as I mentioned, for the block, we would end up with b minus 1 degrees of freedom. And for the treatment, we'd get k minus 1. It's the number of factor levels minus 1 coming from the global mean. For the residuals, what we get is we get something that I wrote out up above, or in the F statistic, which looks like this. But where is that coming from? This, if we expand, it looks nicer when I write it out like that. But when I expand it, what we see is it's actually bk minus b minus k plus 1, or capital N, the sample size, minus b minus k plus 1. So again, the idea being that we have capital N data points, we have to estimate all of the block means, we have to estimate all of the treatment means, but when we've done that, we've kind of have an extra global mean and we can add that back on. So it's, again, a little bit confusing. Another way to look at that, if that intuition is still a little bit arcane, is to note that the degrees of freedom, have to add some, let's say, have to sum to n minus 1. So in a sense, I already have a b minus 1 and I have a k minus 1. And if I add that to this b minus 1 times k minus 1, the answer is b times k minus 1, or n minus 1, which is the degrees of freedom for the total sum of squares. Right, so yeah, let's take a quick break. I'll fill in the rest of this F table, and then maybe we can move on to an example and then go on to the next part of this. And we're back, and in the break, I took a moment just to fill in the rest of the ANOVA table. So there's nothing too profound going on in the rest of the table. Really, the most challenging bit is to try to figure out what the degrees of freedom are before we go forward. So we have the degrees of freedom now. The next column here just becomes the sum of squares column, which is exactly what we computed above. the mean square is just going to be the sum of squares divided by its respective degrees of freedom, and the F-statistic is the ratio of those mean squares, the mean sum of squares. Now, if you note, there's actually an F-statistic for both the block factor and the treatment factor, and this is quite interesting because in practice, we don't typically care too much about the significance of the block factor. We're really interested in testing the treatment factor, but mathematically they can be treated the exact same way. We get our F statistic as we normally do, and we can test for significance. Almost lost my audio recording again. Gotta watch that. Yep, we're still good. Anyway, yeah, so the idea is that the testing for the significance of the block factor can still be actually useful. It can be useful in follow-up experiments, because if we know that a block factor is very significant, what it means is that at least one, or I guess I should say at least two of the levels of that block factor have different response values. And it means that there's variation that can be removed from our data that allows us to better test the treatment. So if we're running a follow-up experiment, what we might learn is that, yeah, we should include that block factor in the follow-up experiment. On the other hand, if it's not significant at all, then we can identify that, you know what, this block factor doesn't matter. It would be like saying that, you know, whether you're a smoker or a non-smoker, there's no statistically detectable effect on how the blood pressure medication works on you. Then in that case, actually, no, there's a slight subtle difference there. It's not how the blood pressure medication works. It would be orthogonal to how the blood pressure medication works. So what I'm actually supposed to say is that having an insignificant block factor would tell us that, for example, there's no difference between the blood pressures of smokers and non-smokers. If that's the case, then we don't have to include that block in a future experiment, and we can save time and funding and money and all of that when it comes to actually testing for everything. Right, so that's more or less the quick overview of the ANOVA table for the complete randomized block design. Now, what I want to do is, well, first just mention something about multiple comparisons and the post hoc test. So once again, I'll say, we can apply a post hoc Tukey test to this model to, I guess, well, compute confidence intervals, but also test for pairwise differences between factor levels. So again, now whether or not we want to do a post hoc Tukey test is really up to the the setting of the experiment and the results that we get. The first thing always to note is that, and I forget if I actually mentioned this the first time we did the post hoc Tukey test, but I will say, note, don't do a Tukey test if F is not significant. This is something that you can sometimes get into trouble with, because, okay, you run your test, you get your F statistic out, it doesn't turn out to be significant, but you still look for pairwise differences. That can be troublesome, because remember, if you fail to reject the global null hypothesis, then what you're saying is there's no evidence to suggest any differences among any of the factor levels. So it doesn't make sense to go and test for differences in the factor levels after that. So that's a little subtlety, but it's really important to be aware of that, because it doesn't make sense to run some of these tests if you don't first reject the global null. It doesn't make sense to test all of these pairwise ones. Yeah, and then also you can apply a Tukey test both to the block factor and the treatment factor. As I mentioned above, we can still test the block factor. And it really depends on if there's something there that you want to test. So for this rabbit data set that we were looking at in the assignments, I really don't care if one rabbit has higher than average blood pressure than another, right? I mean, it's the same with people, right? I mean, every subject in your study will have, say, a different natural blood pressure based on their genetics, their diet, whatever else. I don't particularly care about the difference in the blood pressure of, say, rabbit A and rabbit B. On the other hand, maybe I do want to know the difference in blood pressure between, say, old and young smokers and non-smokers. These could be things that it would still be interesting to report in a final analysis. So you have to always consider, I can do a Tukey test. Do I want to do a Tukey test, or should I do a Tukey test? Or is it just superfluous or meaningless? So these are always good things to note. And if you're reading along in my notes, I put some stuff in there about saying, yes, the denominator changes a bit when you are computing the test statistics, but luckily, I mean, stats packages and R will do all of that behind the scenes. But it is always good to just look at the equations to get some intuition about what's happening there. But another way to get intuition is to look at an example. And that's exactly what we're going to do here. So let me copy that over, assuming OneNote is happy to copy this for me. Let's see if we can do this without ruining my recording, like I did last time. Luckily, you didn't actually see that, so the magic of video. Anyway, here we have an example that I created just of fake data. So I created a block factor. The block factor ranges from -1 to +1. So for each of our blocks, we have a slightly different block mean that will come into play. And for our treatment factor here, we have the first two treatments having a treatment average of 0, and then the last two having a treatment average of 1 and 2 respectively. Again, these units don't really mean anything. It's all just kind of hypothetical. And of course, I generated some IID normal noise here. And I get my ANOVA table, but really before we look at the ANOVA table, we should probably just look at the data itself. And the best way to look at this data is to plot some box plots. So I can copy those over here and maybe make them slightly bigger so that we can see what's going on. So in my notes, my typed lecture notes, I have these box plots. And I wonder if I can stretch it. Yeah, we can distort it slightly by stretching it vertically. Excellent. So here, if we just visually, before we actually run an ANOVA, we could just look at the box plots and say, okay, we have the blocks on the left. Now, when we look at that, we do see that, on the left-hand side here, these seem to be smaller and these guys seem to be larger on average. So it is kind of indicating that something is changing as we move through the blocks. Now, the exact betas are maybe not obvious from here, but at least it tells us that something's happening. And then when we get to the treatment effects, we see the same thing. We see this one and this one are kind of smaller. And at least I don't know what's happening in C, right? C has kind of a high variance. But at the very least, we know that D seems to be much larger. So it's always good to look at this because this tells us that, well, okay, I have a pretty good sense that I'm going to get something significant here, just staring at the box plots. And then sure enough, when we come up to the ANOVA table here in the middle of the screen, what we find is, yeah, we do get very significant p-values, both for the block factor and for the treatment factor. Also take note of the degrees of freedom because we just looked at that before, but it's good to see an example here. Remember, my block here is going to have 6 levels to it, my treatment is going to have 4 levels. So I subtract 1 from each of those to get my degrees of freedom, 5 and 3. And then I multiply those numbers 5 times 3 to get the residuals, degrees of freedom. And again, this is really important to know these degrees of freedom because it's going to save you a lot of headache if you accidentally plug in the wrong formula when you're analyzing data. So I think the degrees of freedom are one of the best things to learn, mainly as a sanity check to make sure that you actually did the analysis the way, or I should say, the computer is giving you the analysis that you think that you're getting, that you want to get. Because it's very easy to type a formula in wrong when you have multiple factors, nested factors, different randomizations and different issues going on with very complex designs. And the degrees of freedom will help keep us sane and let us know that, we're actually testing things the way we think we want to test them. Not 100% of the time is that a fail-safe, but at least it helps us a lot when we're running an experimental design. Now, the interesting thing about we can also do is we can consider, and this is a nice way to jump back to what we did in the last chapter, is that we can consider what would happen if we were to run this experiment without the block factor. So there's nothing stopping you from just ignoring the block factor. So I should be able to get this all on the screen at the same time. Excellent. So now at the top of the screen, we have, we'll say ANOVA. I have to watch that. There's a little tiny box in the corner of my screen, and if I accidentally tap it with my fingers, my recording stops. So one of the things I have to be aware of, or I'm going to mess up this lecture. So this is ANOVA with block, hence my terrible writing here, so apologies for that. With block. And then down here we have our ANOVA without the block. And notice, first of all, well, the degrees of freedom are very different. They still, well, I guess they sum up to 23, which is what we want. It's the sample size 24 minus 1, much like 5 plus 3 plus 15 will also get us 23. So the degrees of freedom always have to sum up to the, well, n minus 1, or the total sum of the degrees of freedom for the total sum of squares. But of note, well, what happens here? Well, this is what happens. Our p-value is it's still significant, but it is larger than what we got up here. Now, if we're trying to be very proper statisticians, we're not supposed to compare p-values, right? We're not supposed to say, this p-value is smaller than that one, therefore it's more significant of a result. That's troublesome. The p-value is supposed to be something that we use to make a decision on. So it's really a binary thing. Is it less than some threshold, then it's significant. If it's not, then it's, well, not significant. But at least in this case, we could claim that, let's say the data, did I get the right? Oh no, I underlined the block factor. Sorry, I underlined the wrong one up here. I was supposed to underline this one. So what we can say here is that the data with the block is significant. That's not how you spell significant. Significant at the 1% level, but without the block, it is not significant at the 1% level. And this kind of gives you an illustration of how the block can help, because in some sense, we're actually losing degrees of freedom by including a block factor. And that will make, that could negatively affect our denominator in our F statistic. So we don't want to include a block just superfluously, because if the block has no meaning to it, we're just going to lose degrees of freedom, and it's going to make our test statistic less significant, or we'll be less likely to reject our null hypothesis for the F test. But when the block effect is very significant, does have a significant effect, what it does is it makes the denominator, which is this guy here. So notice the denominator for our F statistic, which is the residuals. Oops. Yeah, it makes it smaller. And that's really good, because if it makes the denominator smaller, then that means that our F statistic becomes bigger. And then the hope is that the F statistic gets bigger than the number of degrees that are lost, because there's a balance going on here. Bigger F statistic, more significant. Fewer degrees of freedom, less significant. And the question is the trade-off going to give us more power to reject the null hypothesis for our treatment? So there really is this interplay going on here of a trade-off. A very significant block factor will give us more power to reject. A insignificant block factor will actually take away our statistical power. So there is this trade-off to be aware of. Also, one other thing of note, if you're staring at these tables enough, you might notice one other thing. The treatment mean square is 5.266 up here. And look, it's actually 5.266 down here as well. So what's happening here is that, remember, because this is a complete design, we're testing all the treatment within all the blocks the same number of times. The block and the treatment factor become orthogonal to each other, and thus they effectively, don't affect each other. So when we include a block factor, it's taking away the sum of squares from the residuals, but it's not affecting the treatment sum of squares at all. So in our analysis here, the treatment sum of squares doesn't change. But one other thing to notice, if this current page is not messy enough already, I will add in one other crazy thing, which is to note that in the non-blocked ANOVA, we have 23.94 for our residual sum of squares. If we go up here, we see that our residuals now are 9.48 and 14.46. And if we add these two numbers together up to some rounding error, because R just rounds and truncates the decimal places, if we add those two numbers together, we're actually going to get our 23.94 sum of squares. So what the block is doing, if we were to go from, say, one-way ANOVA to a complete randomized block design, what we're doing is we're not touching the treatment sum of squares at all. We're taking the residual sum of squares and we're cracking it in half, and we're keeping some of that for the residuals, and we're taking some of that and we're sticking it into the block factor. And depending again on how good of a block factor we chose, this may improve or hinder our experiment. So yeah, there's a lot of errors here. Hopefully that kind of makes sense. Of course, you can always contact me, come on to live sessions and ask questions if you have any follow-up you want on this. But yeah, we still have a little bit more time at the moment to go through this recording. So what we'll do is we'll actually talk about one sample and two, actually we'll do two more things in this lecture before we wrap it up. So I guess the idea is that even if you've never heard of a complete randomized block design before, you've actually probably seen it in Stats 101 class or 102 in the form of a paired two-sample t-test, or unpaired. I guess paired is blocked and unpaired is not blocked. So when you first learn about how to do a two-sample test in statistics, you probably discuss the idea of paired versus unpaired. So these are two different settings that we have for our t-test. For the paired setting, what we're assuming is that we have two groups and we want to compare their mean. And what we're assuming is that a subject in group 1 is somehow paired with a subject in group 2. An easy example of this would be, say, testing eye drops. Let's say you have dry red eyes, and you want to test medicated drops versus a placebo. Well, instead of just randomly assigning medicated and placebo drops to different subjects, you could give everybody a vial of each, and then they randomly put a medicated drop in one eye and a placebo drop in the other eye. And in that sense, we can treat it as a paired test. So I'm looking at the performance of one eye versus the other, rather than my eyes versus your eyes or somebody else's eyes. And that's going to allow us to, again, control for variation, because maybe my eyes react differently to the medicated drops than your eyes would. So it's a way to control for some of the variation in our experiment. So that's just one example of how we might do a paired two-sample test. Now, mathematically, what happens is we get something that's going to look like this. So for a paired test, we would have our T, I'll say sub P for paired test statistic. The t-test numerator is just going to be the difference in the sample means. So I'll write it as y bar 1 minus y bar dot 2. And then in the denominator, what we're going to get is something that's going to be the standard error. So in this case, not B, S squared. S squared is just going to be our standard, our estimate. I'll write that down in a second. Our estimate, the sample, I guess the sample standard, or the sample variance. And we'll be dividing by B. So I'm assuming, this is assuming group 1 and 2 each have B observations. So that's the sample size per group. I'm using B to rather than N to correspond to what we did above with B being a block. So in some sense, in this setting, every person, if I'm using my example of eye drops, every person is their own block. Sort of I'm my own block. Yeah, and then here, just for the sake of completeness, I'll write down that S squared, our sample variance is 1 over B minus 1, the sum I from 1 to B of, well, in this case, yi1 minus yi2 minus the, well, the sample mean, the mean of the differences, oh, I got this backwards in my, another little typo. I have to keep track of all these so that I can correct them for future versions of these lecture notes. Something that's going to look like that, which is our variance here. I should say, and the T statistic has, well, how many degrees of freedom should it have? If each of my blocks contains, let's say, 2 treatments, then my treatment factor has 2 levels to it, which means that I have 1 degree of freedom, 2 minus 1. Now, for my block, what I have here is I have B blocks, B subjects, say, or B blocks, which would mean I have B minus 1 degrees of freedom. So the residuals would have the degrees of freedom B minus 1 times 1, just B minus 1. B minus 1. So this would just be, and this you could just do from our usual two sample t-test, right? You don't need to understand randomized block designs to understand a paired t-test, but if you actually considered this as an ANOVA table, right, we would have a treatment, a block, and a residual. And as I kind of said out loud, right, we would have degrees of freedom being, if this is, let's say, levels, if this is 2 levels and this is B levels, then following from the table above, I would have 1 degree of freedom for my treatment. I would have B minus 1 for my block, and I would have B minus 1 for my residuals. And also, you probably saw this before. I know you would have if you took, say, the undergrad regression class with me, but a t-statistic is actually just an f-statistic in disguise. If you square a t-statistic, you get an f-statistic. So you could test this as an f-statistic with degrees of freedom 1 and b-1 for the numerator and the denominator. That's equivalent to the t-test in this case as written above, with just single degrees of freedom b-1 for the residual sum of squares bit. Right, so that's kind of the idea of a paired t-test. What happens if we do an unpaired t-test? Unpaired. And we'll block that off in green to make sure we see the difference. So if we do the unpaired t-test, the numerator, I'll say t, let's say up for unpaired, then the numerator here is actually going to be, well, the exact same thing that we had before. It's just the difference in the means. This is always what we're doing when we're doing a t-test, is we're taking the mean of group 1 and we're subtracting the mean of group 2. What changes is the denominator. And the denominator now is going to look something like s1 squared plus s2 squared divided by b. So where in this case, I guess s1 and s2, where we have something like, I'll write it in blue, s1 squared and s2 squared are the sample variances, vars, for groups 1 and 2. Now, there are a couple other different t-tests out there, things for like non-homogeneous variances, unequal sample sizes. In this case, we're assuming we have homogeneous variance and the same sample size as before, and each sample size is b, just to make things easier to do. So also, the degrees of freedom change. So now, the degrees of freedom are going to be 2b minus 2, if I got that right. Yes. Yeah, good. Just making sure I got that right. Because what we have is we have a total sample size of 2 times b, and I'm estimating 2 parameters. I'm estimating group mean number 1 and group mean number 2. So we have 2b minus 2. So those are the change in our degrees of freedom. So as I said before, when we go from an unpaired to a paired, or a no blocking to a blocked test, we actually lose degrees of freedom. And that could hurt the ability to reject our null hypothesis unless the block or the pairing is very important to the data. In this case, we're assuming that it is, and that the reduction in the degrees of freedom will be offset by an increase in the eventual F statistic, or in this case, T statistic that we get out, right? It's how, in our case here, how the denominator changes, which is really the difference between our S squared and our S1 plus S2 squared, which is really how our statistics are changing. So staring at these formula can give you some good information on how they work. And we're going to take a quick break and move on to the final section of today's notes in 1 minute. And we're back with the final part of today's lecture, which is going to be the Tukey 1 degree of freedom test. So this is a different Tukey test, not the post hoc Tukey test or the honest significant differences test. This is the 1 degree of freedom test, which is an interesting little addition to discuss after the in the context of a complete randomized block design. So what we'll do is we'll say Tukey 1 degree of freedom test. Now, there's something about a multi-factor experiment, specifically the complete randomized block design, that I didn't mention earlier. And a key point is that in an unreplicated, we'll say CRBD for complete randomized block design, we cannot test for an interaction between the treatment and block factor. Because we don't have enough degrees of freedom to do that. And to see that, we can note that this is because sure, why not? The interaction term would require b minus 1 times k minus 1 degrees of freedom, with none left for the residuals, or the error sum of squares. So the problem is that if we don't replicate our complete randomized block design, and then we try to test for an interaction between the block and the treatment factor, well, we lose all of our degrees of freedom in doing so, and we have no denominator for the Fstatistic, so we can't actually run a proper hypothesis test. And that's kind of where Tukey's 1 degree of freedom test comes in, is it allows us to test without replication. So, or test a certain type of interaction without replication. But I do want to note that usually we assume no interaction between the block and the treatment. So again, this would be like going back to that blood pressure versus smoking, blood pressure medication versus smoking example I was using earlier in this lecture. The assumption that we would need to make, unless we were to replicate this, is that there is no interaction between the drugs, the medicine we're testing, and whether or not the person's been smoking cigarettes every day of his or her life or not. So it is an assumption we have to make if we want to proceed in this way. It usually is reasonable to assume, but there are cases where it may not be. For example, giving medicine to an older versus a younger person may have a different effect because of how the biology of their systems change as they age. So there are cases where there could be interactions. Now, if we want to test for interactions, well, the most straightforward way would be to replicate the experiment a second time, and that would give us enough data points to successfully test for all possible interactions between our treatment and our block. But repeating an experiment can often be cost prohibitive or just takes too much time to actually do. So Tukey came up with a slight workaround. He said, okay, if I were to replicate my experiment, I could test for any possible interaction between my block and my treatment. But if I don't want to replicate, I can still test for a single type of interaction between my block and my treatment, and just to use 1 degree of freedom to do so. And this is where the 1 degree of freedom test comes from. The idea that we're going to take 1 degree of freedom away from the residuals and use that to test for an interaction of a certain type. Okay, so it gets a little bit more complicated, but let's try this. I think in my notes I used a slightly different notation. I used a 2-factor notation, but I'm going to try to use the notation that I used in the rest of this lecture to be consistent. So the idea is that the interaction model, maybe I'll say the full interaction model, would look something like this. It would be yij is going to be mu plus beta I plus tau j plus, and now I'm going to have an interaction term, which is beta tau ij. I write it as beta tau in parentheses, not to say that I'm multiplying beta times tau, but to say that I now have a new object here, a new effect that has an index, a double index of I and j. So I'm not actually just multiplying the two symbols together. I'm just using it to show that we have an interaction there between these two terms, between these two factors. And then we'd have an epsilon ij. But again, we have not enough degrees of freedom. To actually do this, we would need to replicate this and add on, say, a k and a k to the errors. And then if I replicated it for k from, I think I was using k for the number of levels of the treatment. So forget k, we'll switch it to L. So if I say add on another index L, and I took L as my replication, 1 to whatever n, then I could actually test for this general interaction term. But with Tukey's 1 degree of freedom test, a freedom model, then what I'm going to do is I'm not going to replicate. Instead, we're going to add on a very specific interaction term. And the interaction term in this case is going to be a multiplication. It's going to be lambda times beta I times tau j plus epsilon ij. So here, I multiply together, and what I'll also say here is that here lambda is a new one-dimensional parameter. And we have to estimate that. Just like we do in stats, we now have one more parameter in our model. It takes 1 degree of freedom to estimate, and we can test for, well, if it's different than, say, 0, to know if there is some type of specific interaction. And this specific interaction is a multiplicative one. It's saying that there's some multiplicative interaction of beta I and tau j. And again, I want to emphasize this is different than the full model. In the full model, we could have any type of crazy interaction between tau, beta, and tau. It doesn't have to just be multiplicative. It could have some other peculiar shape to it. The idea of Tukey's test is we take perhaps the simplest type of interaction that we maybe the simplest and also the most common type of interaction that we may see in practice, which is, yeah, there's some multiplicative effect here between beta and tau, and we add on one parameter lambda that we can then estimate. If lambda is 0 or not significantly different than 0, then we can say, we don't see this specific interaction in our data. If lambda is significantly different than 0, well, then we actually can say that there does seem to be evidence of an interaction here. We can either stop there, or we could replicate our experiment to then get more data to more properly estimate the interaction effect. So this is kind of like a quick test you can do to say, I really don't want to replicate my experiment, but I don't know if there's an interaction there. So you can use Tukey's 1 degree of freedom to kind of say, okay, I didn't see anything too significant there, so we're just not going to replicate. Or it's, something actually is happening here between my block factor and my treatment factor. I better replicate to learn more about it. Anyway, if we do this, and luckily, well, actually, I'll get to that in a second. We're going to get a new ANOVA table. And it's going to be, well, a little bit more complicated than last time. So in this time, we're going to have a, well, treatment sum of squares. We're going to have a block sum of squares, just like before. we're going to now have a lambda sum of squares, which is the new one, and we're going to have an error sum of squares. So when we go through this, again, the most important is kind of the degrees of freedom. And what we get is the same thing as above. We have our k minus 1. We have our b minus 1. We have a single degree of freedom for lambda. And now for the residuals, or the error sum of squares, we have the same thing as before, but we have to subtract the 1 that we got from estimating lambda. So this is kind of the new thing we have here, is that we have to subtract 1 degree of freedom from our residuals. And the sum of squares formula are kind of the same, but they become a little, the lambda one is quite annoying. So for the sum of, I'll say sum squares, well, what we get here is a couple things. This is the, I'll say same, and this is the same as above. So nothing actually changes in how we compute the sum of squares for our treatment or for our block. But we have to compute a sum of squares for lambda. I'm not going to derive it because it's kind of annoying. I'm just going to write it down. I'm not expecting you to memorize this or anything, because it would be silly. I hate memorizing formula, and I think it would be silly to try to memorize this anyway. I mean, I have it in front of me, so I'm not memorizing it. But it is worth to write down just so we can stare at it. And in this case, we take I again from 1 to, I think, B, if I remember my indexes correctly, and J from 1 to K. And what we have here is now we have Yij, and we have beta hat I and tau J hat. Again, if you're reading along in my written lecture notes, I'm doing it in a slightly different case, because when I first did this course a couple years ago, I skipped this section. I didn't actually think about including it until after I did two-way ANOVA. And then I thought, oh, you know what? We probably should do this 1 degree of freedom test, but it fits more naturally in this section of my notes. So I'm changing the notation that I'm writing down in right here. Anyway, yeah, so we have that in the numerator, and then we get this denominator term, which is going to be the sum of the beta hat I and the sum of the tau hat J. And this whole thing is, these are squared, and this is all in the denominator. So yeah, the formula is pretty terrible, but it's not horrendously bad. What you basically have to do is estimate the beta hats and the tau hats. These are just the, these things, right, are just going to be the category, I'll say not sample mean, but the category means. So there's a bit of a inner product type thing going on here. If you like mathematics and linear algebra, then there's kind of a bit of an inner product, in the sense that we're considering we're considering beta times tau weighted by y, and in the denominator, we're just doing the sum of the squared betas and the sum of the squared taus. So if this object is large with respect to the residual, the error sum of squares, then we can identify that there is a evidence of an interaction between our block and our treatment. So the Fstatistic, let's switch back to black. The Fstatistic is going to look something like the sum of the squared lambda divided by the error sum of squares. Now, in the numerator, I'm dividing by 1 the degree of freedom, so I'm not going to include that. But in the denominator, I have to divide by its degrees of freedom, which is this b minus 1, k minus 1 minus 1. And skipping the actual derivation, we claim that this also has an F distribution under the null, with the corresponding degrees of freedom. I guess technically you could think of it as a t-test if you took a square root of everything, but we could just formulate it as sums of squares in the form of an f-test. Right, so then luckily R does this for us. This in the DAE package, which I believe is design analysis experiments, design and analysis of experiments package. And the function is the Tukey dot 1df function. So you can try this out if you have your own data that you're looking at, and it'll give us a sense of, is there actually an interaction here? Again, especially when we have an unreplicated randomized block design like this, it's very typical for the experimenter to just say, I'm a smart person, I've been studying this field for a while, and I declare there's no interaction between my block and my treatment, especially based on, say, past studies. You could lean on and say, given past studies, we do not believe there's any interaction here, so we don't need to worry about testing for that. But this just gives you one way to do some type of a test for interactions. And yes, I did try this, I think, on the rabbit data set in my notes. So in that case, it was for dose and treatment. Well, we'll save that maybe for an online assignment and not discuss it directly in class. But yeah, the idea is that you can use this to check for when you have unreplicated data. And also this type of logic extends when we go beyond just a single block and a single treatment. We could have multiple treatments, we can have multiple blocks, and then we can actually test for some pairwise or triple interactions, but we can't test for the giant interaction of all the blocks with all the treatments. Luckily, the more complex your experiment gets, the less likely you're going to have some crazy high order interaction term. We're going to discuss that more when we get to factorial experiments later in the notes, chapter 4, I believe, in my lecture notes. But for now, I think I've spoken enough about the complete randomized block design. So we're going to end it for today. Remember, today what we did was we introduced the idea of having a block factor with a treatment factor. We kind of compared that to the paired versus unpaired t-test like you would have done in a Stats 101 course. And we also learned about this kind of cool tool of the Tukey 1 degree of freedom test that we can use to look for interactions when we don't have a replicated experiment. Next, we're going to move on to two-way, even more complex settings, including two-way ANOVA, Latin squares, and a relative, you could say, of the complete randomized block design, the balanced incomplete block design, where we remove the condition of completeness, but we still have some other things that we have to worry about in that case. So with that, I will see you in the next lecture.